Welcome! In the picture, you see the wind blowing over the Netherlands. Here in Delft, the wind is blowing northeast 4. We can describe the wind using a vector. A vector consists of two components, a direction and a length. You see these components in northeast 4. The direction is from the northeast, so to the southwest, and the length is 4. Moreover, a vector does not have a fixed starting point. A northeast 4 here indicates the same vector as northeast 4 at your location would. In this example, you see that you can use a vector to describe a flow of water, but of course wind is a flow of air, or electric charge down a wire, or a flow of people moving from one place to the other, work as well. Indeed, velocity, which is a vector describing how fast you are moving and which direction you are moving in, is in a way one of the most basic examples of a vector. Related to this is the displacement vector, which is the vector on a plane from one point to another. Another important concept that can be described using vectors is forces. The gravitational force on me has a direction, points downwards, and a size, some 600 Newton. Can you think of another concept that has a length and a direction so that it can be described using a vector? In the next video, you will learn how to describe vectors using numbers and coordinates. But in this video, you will develop a bit of an intuition about what the things that you will be calculating actually mean. So don't worry if you don't see any numbers today. First, a little bit about notation. As vectors are not numbers, we want to easily be able to distinguish between them. Thus, we typically use some sort of special notation to warn that we are dealing with a vector. In print, vectors are often printed boldface and upright, as opposed to italic. But this is really hard to do when writing yourself. So alternative options are to underline vectors or to put a little arrow above a vector. The last one is my personal favorite, as a vector is an arrow after all. For special kinds of vectors, even more notations are used. For example, by placing a caret on top of the letter. Sometimes, when you are sailing, the boat is lying dead in the water because there is no wind. On a windless day, we still want to describe the wind using a vector. The length of this vector is clear, it should be 0. But what is its direction? Well, if there's no wind, it does not have a direction either. So the wind is blowing along a vector of length 0 and without a direction. This is called the 0 vector, which is the unique vector which does not have a direction. This vector is written as just the number 0 with the "this is a vector" notation. In this case, a bold 0. Now, consider 3 points in the plane, A, B, and C. 2 points define a vector, the vector from one point to the other. The vector from A to B is called simply AB. What happens if you first move from A to B and then from B to C? That's right. Effectively, you've moved from A to C. This explains the definition for vector addition. The sum of vectors AB and BC equals the vector AC. In general, if we have two vectors which are placed head to toe, their sum has as starting point the starting point of the first vector, and the endpoint is the endpoint of the second vector. Consider the sum on the right. Recall that vectors don't have a fixed starting point. So if we want to add two vectors which are not head to toe, we can shift one, or both, of them to place them head to toe, and then do this addition. A typical application of this vector addition is adding forces. Consider this cyclist on this heavily sloped track. Gravity is pulling him downward, while the track exerts a force perpendicular to the track, that is, to the top right. What is the total force on the cyclist? Well, we need to add these two vectors. The sum of the two forces is obtained by placing the vectors head to toe. Together, they generate the orange force to the right, which helps the cyclist to easily round the corner. Another operation on vectors is the scalar multiplication. A scalar is just a fancy word for a regular number. We use scalar to distinguish it from a vector. Thus, scalar multiplication is a multiplication of a vector with a number. What happens if you multiply a vector v by 3? The direction of the vector stays the same, but the length is tripled. Thus, it is the same as v plus v plus v. But of course, we can now also halve a vector. Indeed, multiplying by any positive number just scales the length of the vector by that number. We can also multiply a vector by -1. If we multiply by -1, we flip the direction of the vector to its opposite value. The length is multiplied by the absolute value of -1, that is 1, so it stays the same. In this way, we ensure that v plus minus v equals 0, where we use the 0 vector, the unique vector that has length 0 on the right hand side. If we multiply by -2, the direction is flipped and the length is multiplied by 2. One application that involves scalar multiplication is Newton's second law of motion, F equals m times a. Here F is a force, and as we explained, this is a vector. M is the mass of an object, which is a scalar, and a is the acceleration, which is again a vector. Indeed, acceleration has a direction as well as a size. In the next video, you will learn how to describe vectors using numbers. But for now, try to just think about arrows in the following exercises. Goodbye.